slipping, dislocation, twinning, and all those things. And for different other materials, there are different mechanisms, but the mechanics equation will be same for all. Also, the damage mechanics, when we will deal with that, they will also be applicable to more or less all types of materials. Okay. That is mechanics part. Then you have fractography. So there are some signatures which is there on the broken sample of the material, and those signatures can be evaluated quantitatively and qualitatively for understanding that how the fracture would have happened. So that is post-mortem. Okay. You have a broken sample, so you look at it under optical microscope with naked eye and under scanning electron microscope, not under TEM, but under scanning electron microscope, and then you can look at the fracture surface and you can tell whether the material was oriented in some direction, whether the material broke by the mechanism of ductile fracture or brittle fracture. So that is quantitative fractography. Also qualitative fractography is there, so that we'll discuss, but first we need to understand what is fracture mechanics. So what do you think, when did this study of fracture mechanics started? How old is this? No idea? Take a guess. When do you think people started studying about fracture mechanics? Guess, Karan.
Maybe about century ago.
Century ago. So 1900.
19th century.
19th century will be 1800 something. We're talking about 1800. No? Around 1800. Before that?
Iron Age, sir.
Iron Age. Oh, Baba. Well, so elastic theories and things were there, but specifically talking about when you have crack in the system, that started for the first time in 1921. So that was even after Gandhi. So when Gandhi was trying that Asayog Andolan and Namak Andolan, in those days somebody started with cracks in the material, and that was Griffith. Okay. So Griffith is the first one which is reported to study about fracture mechanics, but the fracture event has been there as long as the space is there, as long as early as any material existed, there would have been fracture. So first image of something related to fracture people have found in the notes of Leonardo da Vinci. So that is 1200th century. Okay, and in that note you will see a sketch which is a wire, and you have a bucket here, and then you have a box from which sand is being poured in this bucket, and just below this you have a hole. And what is the specimen in this case? What is specimen is being tested? Wire, yes. So he has drawn this sketch. It doesn't mean Vinci has done it. So Vinci reportedly has worked with many different people who were experts in different areas. So he has learned different style of painting. We don't know if he discovered the style of painting himself or he learned it from somebody. He has also studied engineering with different people. So that was the period when Renaissance was happening in European countries. So a lot of scientific discoveries were happening. So in those days he was, as an apprentice, went to different people. So he has drawn this image where the wire of iron is being tested, and in the bucket you are pouring sand. That means you are increasing the load. Okay. So as the load increases, the wire will get extended, and after some point it will fail and the bucket will fall in the hole, and you collect the sand and the bucket and measure the weight, how much weight was there. You know the diameter of the wire, and so you can calculate fracture stress. Okay, and the result of the study was that this stress was different for different diameters of wire. If you change the diameter of wire, not the force, the stress will be different. Why it will be different? It's the same material. If you are changing the diameter, why the force, or sorry, the stress will be different?
Change of surface area.
Surface area? What is the relation of surface area with fracture stress? So when we do stress strain tensile testing, then you get for one material you get a stress strain diagram, okay, and then it breaks at some point, that is your sigma f. Okay, so if the material is same and if you change the diameter of the sample, will you see a different stress strain diagram or you will see the same stress strain diagram? So then why he is getting different stress value? He is getting different stress value because it's what kind of fracture you think was happening in those days in wires? No, brittle. Not completely brittle, but brittle fracture, because those days the samples were made up of iron, not steel. So it is cast iron. So the fracture is brittle, and the brittle fracture is dependent on the size. There is size effect in ductile fracture also. And why size matters? What is the argument in this case? What could be the argument that different sizes will give you different stresses for fracture?
It is per unit area.
Yeah, that is normalized. Yeah, that's why I'm asking you. Otherwise, I wouldn't have asked.
Sir, it is per unit area and it will be for the full material. As material is increasing, strength will also increase.
Why it will increase? So if the material, I test two different samples of different dimensions, will I get different stress strain curve?
So, sir, the bucket will hold the force and for the.
Yeah, the force will be different. But what about the stress? It should be same. He was getting different. That is the question. Why he is getting different values? So if you have a wire and then you have loaded it, so it is going to elongate elastically and then it is going to elongate plastically, then there will be necking. Where will be necking? Where will the wire neck?
Just before fracture.
Where? Which
When?
location?
Where there is a void or
And where will the void come? Although it's not ductile, but let us say voids are coming, a little bit voids will be coming. So where will it come? So also in those days, steels were not very clean. Iron was also not very clean. So you have a lot of carbides in it. And you know that cast irons has. So you have white cast iron, grey cast iron, spheroidal cast iron. Okay. So in cast iron you have flakes of graphite. Right? Sometimes carbide. Right? So when you have carbide or graphite, then they are in which form? They are in the form of flakes unless you make it a spheroidal cast iron, right? Or globular cast iron where carbides are in a spherical shape. If you don't do that, even if they are spherical, that is okay. The same phenomena will happen. But you have flakes of carbide, not of this size, but something like this. So now tell me where the nicking will happen, if at all it happens. So these will act as stress raisers, right? They are loaded. So initially they are in continuum, okay? So whatever load is there is being transformed to the matrix as well as the inclusions. Okay, so you have inclusions, you have carbides, all of them, the stress are same. If you draw the stress strain diagram of just graphite or carbide and iron, then they will have a huge difference, right? So graphite will be very brittle, also the elastic modulus might be different. So that will go something like this, a little bit of plasticity if at all, and then it will fail, right? So at same amount of stress, for example, if I have same amount of stress, both of them will be having different amount of strain, right? So graphite is not stretching that much, iron is stretching too much, so there is strain incompatibility, and there will be either delamination or the graphite will break. Okay, so the fracture stress for graphite or carbide or inclusions are inclusions in the form of oxide, so their fracture stress is also very small. So all of them, most of them are going to break. Okay, they are broken. So now there is a surface, now there is no load on it, so that acts, it will act. If it is ductile, then this will act as a void. If it is brittle, they will act as a micro crack. Okay, suppose the surface between the graphite and the matrix has delaminated, that could happen. But in case of very brittle particles, the particles themselves will break and there will be a crack there. Okay, so those micro cracks are there. So you have a lot of micro cracks now, and some of them, all of them will grow, some of them will lead. Okay, so maybe two of the micro cracks will join, will become bigger, and then they are bigger, so they will lead, they will propagate more, and then the material will break. Now tell me why different sizes are giving you different stress values.
Greater the size, more the breaks.
Yes. So you have more number of cleavage initiators or stress raisers if you are increasing the diameter of the sample. Okay. So after Vinci, you have English in 1911, probably, I'm not so sure, and he talks about holes, elliptical holes in material, in plates, okay, and how the stresses will develop if there are holes. So still not cracks, but holes. Okay, so he talks about when you have bolts or when you are drilling a hole, then the stress will raise or not, and he derives the theory based on theory of elasticity. That is what Griffith uses for his derivation of. So Griffith applies thermodynamics that if you have a specimen which has a crack in it of certain size and the thickness is unit, okay, so all the calculations or derivations are happening in 2 dimension. 3 dimension effect is not taken care of right now, and all the 3 dimension problems are broken into plane stress and plane strain. So that's how they solve it. Okay, so you have stress applied on this plate, and this dimension is infinite. Okay, so the width of the specimen is too high, so effect of width is not computed, calculated. Okay, thickness is unit, and you have a hole which is elliptical, because an ellipse, if you use in equation, you can make it hole and you can make it a very sharp crack by changing the major and minor radii of the ellipse. Okay, so so for this, if you load the sample, it goes to certain height, and if there is a crack growth, now in the same sample, if the crack grows by a certain amount, then the load will drop. Will it not? The force which you are, so initially you load this plate, you apply force on it, and you keep on increasing the force like Vinci is doing. Okay, then the crack grows to certain amount. What will happen to force? Will you have to increase the force now, or will there be a sudden drop in force? Why? Why will there be a drop? You can also imagine the displacement control testing. So there you are applying displacement on the specimen instead of stress. So you say that I am stretching this specimen increasingly. So initially 1 mm, 2 mm, 3 mm you are going on. So as you increase the displacement, the force also is increasing, right? Then there is a crack growth. but you are not stopping, you are still increasing the displacement. So with crack growth, the force will drop or it will keep on increasing. Why?
This will drop.
Why?
Sir, because total energy required will be less.
Why?
Sir, because now surface energy surface energy will be increased, but it will not increase in that quantity as much as sir mechanical energy will be required.
And incorrect. Surface energy will increase,
Yes,
fine,
sir.
but that is not being recorded in the form of load or displacement.
Yes, sir.
In force and displacement measurement, there is no measurement of surface energy, right?
Yes, sir.
So you are saying that we are applying some amount of energy.
Yes, sir. But now we don't need that much amount of energy.
Why?
As it was initially, sir. So initially, with growth of crack, sir, more surface energy was was needed. Okay, but now, sir, as crack has already grown, sir, that much surface energy will not be required to further grow it.
So that much surface energy is not required.
Yes, sir.
Before that, surface energy was required.
Sir, with crack growth, it is increasing. It's
What is increasing?
surface energy.
Okay.
Okay.
Yeah. Then
So surface energy is increasing at the cost of elastic strain energy. Elastic strain energy
surface
is increasing.
energy is increasing at the cost of elastic strain energy. That is fine. So
So elastic strain energy will decrease
why?
because surface energy is increasing.
Why surface energy will increase?
Because the surface area is increasing. Surface area is increasing for this pole.
Okay.
So energy is
Do
conserved.
you understand?
So there is an additional surface.
Yes.
Where we are considering this.
Yes.
Crack. There are two surfaces.
Hmm.
Additional surface is there. So
So
total surface energy is increasing because
okay.
due to
Fine.
increase.
So you can just see that when the crack was here, okay, on both sides you have, let us say, X millimeter of material which was intact, right? When the crack has grown by 2 millimeter, now you have only X minus 2 millimeter which is intact, right? So less material is intact. It is equivalent to having a wire which Vinci is testing of a smaller diameter. Now diameter has decreased, right? So for this decreased diameter, for the same amount of stress, the force is going to decrease or increase? It is going to decrease. Is it okay? Do you understand? Now there is less material which is intact, okay? So you need less force. So there will be a drop in force, right, for the same amount of displacement. If you want to extend or expand the specimen by same amount for two different specimens of different crack lengths, will need different amount of forces. Which one will take lesser? The one which has larger crack length, right? Because less material is available to take the load, okay? So now, so these are two specimens here, one specimen and second specimen, and the first specimen has a crack length of A1, second one has A2, and A1 is less than A2, okay?
Yes.
Yes.
Sir, as we reach crack पे पहुंचने के लिए सर हमें मटेरियल को डिफॉर्म करना पड़ेगा,
हाँ हाँ
तो उसके लिए तो डिफॉर्मेशन एनर्जी ज़्यादा होती है क्रैक से।
क्या
सर मटेरियल को डिफॉर्म करेंगे तभी क्रैक प्रोपेगेट होगा।
करेगा? हाँ करेक्ट।
तो उसके लिए तो स्ट्रेस इंक्रीज ही होगा ना सर, पहले तो डिफॉर्म करना पड़ेगा, क्रैक के लिए तो एनर्जी कम चाहिए।
हाँ करेक्ट, डिफॉर्म करने के लिए एनर्जी ज़्यादा चाहिए। यस,
तो स्ट्रेस तो इंक्रीज ही करना सर, मटेरियल
स्ट्रेस इंक्रीज करेगा फिर डिक्रीज करेगा। एज सुन एज देयर इज अ क्रैक ग्रोथ, स्ट्रेस विल ड्रॉप। But before the crack propagates, you are saying that initially this is the crack length. In order for this crack to grow to that extent, there is some deformation. and that deformation is going to consume some energy, right? That part is ignored by Griffith. So in terms of Griffith, you are in future. Okay, right? So and Griffith is doing his tests on glass.
Brittle material.
So glass will not consume, so it will consume insignificant amount of energy. So that is not observed in the experiments. Okay? So when you test cast iron or very brittle, for example graphite, it's not going to consume any energy plastically, right? So everything is going to be elastic and fracture, no plasticity. Whatever plasticity is there, that is so small that it cannot be measured. Okay? What you are saying is correct, but that is in future. That happens after Griffith. Okay? Good. So where were we? So we have two samples and two samples at two different crack lengths, and even if there is plasticity, okay, if this crack has to grow to that extent, you will need more force for plastic deformation a little bit, but then the load will drop. It must drop, because so in this case maybe with plasticity you can say that the force will be a little higher in comparison to what? In comparison to the final crack length. Whatever energy is needed for the final crack to extend to the same displacement, a little more will be needed because that is going in plastic consumption, right? So here there are two different specimens, but now assume that the first one is changing through the second one, and this is an exaggerated view. Okay, for 2 millimeter of crack extension, the two curves will not be that distant for the same material. They will be very close, but we will not be able to see it. So this is an exaggerated view. So now this sample, let us say, grows to a crack length of A2. In order to do that, it will have to, so how much energy is available? Initially it was here, so there was this much energy. What is that? So that is half into force, whatever force, so this is P1, let us say. So P1 delta 1. This is the amount of energy which was available when the crack was A1. Now it has grown to A2 and the amount of energy is this, right? Sorry,
P2 delta 1.
but delta 1 is equal to delta 2. So P cannot be P1, okay? So it will be P2 delta 1, right? So the energy which was there when the crack was A1, certain amount of energy is gone now. And where is that gone? In creation of surface. That part you have understood, okay? So if you ignore plasticity, then the crack has acquired more surface. So this part has increased to that part, right? So more surface has been created, and that surface creation needs energy because you have to put atom at the surface. Atoms don't want to be on the surface, okay? So you are forcing them to be, and that's the end product. Before that, any material will try to move and flow so that we don't have to make the surface. That's what atom thinks probably. But at the end, if you are not stopping the force or displacement, surface has to be created, and then you have to put some atoms at the surface. That will require some energy, and that energy is coming from the elastically stored energy, because elastic energy is reversible, right? If you unload, it will be gone. So that energy is only can be used for surface creation. Even if there is plastic deformation, plastic energy cannot be used for surface creation because that is dissipated, that is consumed by the material, that is irreversible, okay? So that's what Griffith says, and he calculates the change in potential energy with change in crack length. From the equations of English, he derives this final formula which is 2 pi sigma square A by E. Okay? And then this crack length, if you assume that 2A, so this is A, that is A, so that is 2A, and then you describe that as the total crack length, so that becomes pi square sigma square C by E, where C is equal to 2A. Okay, and then from this you can say that for fracture you need a critical value of this, right? Critical value of rate of energy release per unit crack length. And when will that happen? When the fracture stress is reached. Okay, so that you can calculate from this. So this is designated as G, and the critical value of this becomes GC. G because Griffith. Okay, so this is fine. Then now how do we calculate this experimentally? How do we calculate the value of GC experimentally? So energy can be written as half into force into displacement. If the slope of the curve is m, which is the stiffness in force displacement curve, then P is equal to m delta. Right? Now replace delta with m, then what will we have? Half P square by m. Right? In that curve you see that delta is constant. So what is delta? Delta is P by m. Right? So delta 1 is equal to delta 2, that means P1 by m1 is equal to P2 by m2. Okay? So then if you do the derivative, so this is constant, so if you do the differentiation of this, that is going to be 0. Okay? So do the differentiation. So what will that be? Del P by del A 1 by m plus del of 1 by m del A, and then you will have P here, right? That is going to be 0. Correct? Now what do? We have to find out del U by del A. So we have to differentiate this now, right? So del U by del A will be the differentiation of this. So half I will take out, and then I will have what? 2P by m del P by del A plus P square by 2. 2 is out. So P square, and then what? Del of 1 by m by del A. Right? So now we have to replace del P by del A from here. So del P by del A will be what? M into del of 1 by m by del A. Anything else is coming? No, no. P is there. So PM. P into M, that and that. Right? So del P by del A is equal to that. So that if you put here, then we have 2P by M, and then we have into minus PM and del of 1 by m del A. Anything is missing? 2p by m, pm, blah blah blah, and then this. So what will we have then? Del u by del A equals, so m will cancel out, Then we have 2p square and, right?
Yes.
2p square, and we have p square there also, right? So what is the final product? Let us write down there. Half, and then we have 2p square, 2p square del of 1 by m by del a, and we have minus here, no?
Yes, sir. Minus 2p
So this is minus,
Minus.
and then we have
plus p square.
p square right? So then we'll have negative of this, and that's it, right?
Yes.
So this will be the final value, and if you want to find out the critical value, then that will be equal to P max square right? A very short assignment will be for you guys is to derive the same thing when instead of displacement you have force constant. So here we have done for displacement constant, then you assume force constant and derive the same thing, and then let us know what do you get. Okay? So Griffith not only does the mathematical calculation, he also does the experiments on glass, as I said, and he relates this and he finds absolutely stunning results, and that is published in 1921, and everyone is happy with Griffith. Later on, what you said, what's your name? What? Sharman. What you said is that there is some energy which is consumed in plasticity. So that modification in Griffith equation is done by whom? So what was our equation? So GC was pi sigma square C by E, right? So then sigma F becomes GC E divided by pi C square root, right? So Oro1 adds one term here, and that becomes energy which is used in plasticity, and that's it. Okay, and it's done. And for a very long time, at least 20 years or so, the same equation is used in design. And no changes happens, nothing happens until a naval officer starts working. Initially he starts working on dynamic fracture. So when bullets are hitting things, then how do you make an armor for a tank, or how do you make an armor for body? On those things this guy starts studying, and then he applies what is available is Griffith. And he finds out that it's not working because material has evolved now. So now you have a lot of materials which can plastically deform, and they can deform very, very heavily. Okay? So you can't ignore it. And the equation is not working. So what does he do? He goes to his supervisor. No, there was no supervisor, right? And he was not doing a PhD. Okay, so he had to solve it. He was a naval officer and he had to solve it. It's not just कि मेरा काम नहीं है, किसी और को दो, ऐसा नहीं, उसको करना है. Okay, so he reads all the elasticity calculation theories and he develops something. And whom are we talking about? Whom are we talking about? No idea? We're talking about George Irwin. and you should read his story. So not a big story, just read it on Wikipedia, what he has done, where was he deployed, and what and all calculation and other things he did. Okay, it adds on to whatever you are studying. If there is a story, then it helps. Also in your PhD, a little bit of motivation. Also motivation will not stay for a pretty long time. So you will lose it after half an hour, but it's good to know. Okay, so before we go to what George Irwin does, we will have to understand a few things. And one of the thing is equilibrium when we have stresses, and that is pretty simple. So, and in very brief, I have told you. So instead of 3 dimension, if we look in 2 dimension, so we have, let us say, sigma xx here. So this is what? X, and this is y. Okay. So we have sigma xx, and now assume that sigma xx is increasing in x direction. It's not constant. So what will be the stress here? Because there is a little bit of change in dimension there. Okay. So I will have sigma xx plus whatever is the rate of change of sigma xx into delta x. Right? Then I will have tau x y or tau yx. So this will be changing with y direction. Okay. So if this dimension is delta y, then here I will have tau xy plus del tau xy by del y into delta y. Right? And this is of course negative, and that is positive if we take that as positive. So this is negative, that is positive. Now you do force balance. Why are we doing force balance? Because we don't want it to rotate. Okay? So we start with an assumption that things are not in equilibrium, and then we put a constraint that it cannot rotate. Then we get the equation of equilibrium. Okay? So if you do force balance, what will you get in x direction? So we will have minus sigma xx into the area. So what is that area on which it is working? So delta y into b. So delta y into the thickness of the body. Okay? And then we have sigma xx plus del sigma xx by del x, delta x. This will also be multiplied by delta y and b, and then we will have minus tau xy into what is the area for tau xy? Delta x into b, right? So we have delta x into b, and then we have tau xy plus del tau xy by del y into what was that? Delta y into delta x into b, and this will be equal to 0 because I don't want any force, I don't want any net force, right? So then you tell me what will be the final expression for this? So delta yb is there. Are we missing something here? Sigma xx, this bracket is, no. This is as it is, right? So sigma yb, negative of sigma xx into delta yb, and here you have positive of sigma xx into delta yb. So this will cancel out, right? then tau xy delta xb, and then you have positive of tau xy into delta xb, right? So this will also cancel out. So what will you have? You will have this term. So that delta of sigma xx by delta x into the 3 dimensions, and delta tau xy by delta y into the 3 dimensions, right? So those delta x, delta y and b you can throw away because you know that they are not 0. So whatever remains is del of sigma xx by del x plus del of sigma xy by del y, right? This equals 0. Similarly, yeah, tau and sigma same. When they are shear, we write tau. Okay, so if you do force balance in y direction, you will get one equation. If you force balance in z direction, so you will get 3 equations, right? And these are the equations of equilibrium. Okay, so let us write those also. So sigma y by delta sigma, sorry, delta y plus delta yx by delta x equals 0. Then you will have sigma 0. Okay, so let us take 2D problem and take 2 equations for now. Okay, 3 dimension you can do. Fine. Apart from this, we also have strain compatibility equations. Okay, what are those? And what is strain compatibility? So strain compatibility. So if epsilon xx, so how many stresses we will have? In how much time do we have? Okay, we have some time. So epsilon xx, epsilon yy, and we will have gamma xy, which is equal to half of epsilon, not half of, double of epsilon xy, right? So epsilon xx is what? Del u by del x, right? And this is del u by del y, and this is not half now, so it will be double. So del u by del y plus del v by del x. This much we know. For strain compatibility, you have to take double derivative of this. Okay. So the rate of change of epsilon xx in y direction will be how much? If you calculate from this, that will be how much?
Del 3u
Del 3u
by del x or del y square.
del x del y square. Okay. Then if you do epsilon y del x square, then that will be del 3u divided by
Del y
del y del x square, and then what will be epsilon xy divided by del x del y. What will be this?
del 3.
So then half will go there, no? Because we are doing this derivative. So derivative of this with respect to x, what will be that? First, do the first derivative of this with respect to del x. So del epsilon xy by del x is equal to how much? You have del u by del x del x square, no? Del 2u by del y into del x plus
Del 2b by del x square.
del 2b by
Del x square.
del x squared, and now you do this, and what will you get?
Del 3u by
Half
del 3u
del 3u
by del x
by, now we are doing with respect to y, right?
Del x
So del x del y square plus del 2b by
Del 3.
del 3b by del x
square
del y, right? So what is del 3u by del x del y square? This. So you put this here. And the second term is that this is v. Okay? So then we can write del 2 epsilon xy by del x del y is equal to del 2 epsilon xx by del y square plus del 2 epsilon yy divided by del x square. This is a strain compatibility equation for 2 dimension. In 3 dimension you have 6 equations. Okay? So it, in physical sense, it means that if you have a shape, okay, and then you have the strains in all different directions, right, and so it will deform, but you have to maintain the connection in the deformed state also. If you don't, then this will deform like this and you will have an intersection. So those equations fulfill that. This should not happen. In deformed state also, you must have connectivity. So this is strain compatibility means. Okay? So I have 2 minutes. In those 2 minutes, what are my force balance equation? Where are they? Here, no? So can you tell me a function, if it's a weird function which I take and these equations are satisfied? So if I take sigma xx is equal to del to phi, where phi is a function, and del y square, and sigma yy is equal to the double derivative of same function with respect to x square, and sigma xy is equal to negative of del to phi del x del y. I don't know what phi is, but phi is a function, and if the phi satisfies these equations, and if you plug them here, you will see that they will automatically become 0. Okay? So del sigma xx by del x will be del to phi by del y square del x, right? And then del xy by this, you will have that.
So it will be 3 times del q. If you take
Yeah, you can do del 3. So del sigma xx by del x will be how much? Del 3 phi by del y square del x, right? And then you have minus of this, and what is this? Del 3 phi by del x del y into
del x del y square.
del x del y square. So then it becomes 0 automatically, right? Same thing if you plug in second equation, it will automatically become 0. So mathematically, if you can find a function which satisfies those, so if stress can be defined in those terms, then these are taken care of. And you will also see in the next class, will not see, but because that derivation is little different. So strain compatibility equations, which is that, or you can do that also, will also be satisfied with a similar function. For elasticity, we have defined it for stress. From stress we can calculate strain, right? So epsilon ij is equal to 1 plus mu by e, sigma ij minus mu by e, sigma xx plus sigma yy plus sigma zz. You use that relationship and find out the value of epsilon xs and then plug them here with the definition of function in terms of phi, and you will see that they also are getting satisfied. Okay? So then the end will be to define phi. What should be phi? Okay? So that we'll do in next class.